Okay, let's talk about organic chemistry. OrgChem 101. If you've been through it, you probably remember that feeling. Maybe dread.
Oh, definitely. It often feels less like learning and more like surviving a massive info dump.
Exactly. Like this huge mountain of reactions, weird named mechanisms, endless facts, all just stuff to cram in, endure, and then, let's be honest, forget immediately after the exam.
That's such a common experience. I remember students just trying to make the arrows work to get the product, not really thinking about why the electrons move that way.
Yeah, like reverse engineering it without understanding the cause and effect.
Precisely. And, the way it's traditionally taught kind of encourages that. You race through so many different reaction types without really nailing down the fundamentals first.
I definitely remember that feeling. Like trying to memorize a cookbook with 1,000 slightly different recipes. The sheer volume of stuff can push actual problem solving aside. Instead of a library of facts to memorize, what if organic chemistry could be more like an operating system? Something logical.
That's the idea behind the source material we're looking at today. It proposes this really elegant alternative, a simple set of priority rules.
Okay, priority rules. The goal here, as I understand it, is to learn how to think mechanistically before you even get bogged down in specific named reactions.
Exactly. It's about empowering you, the listener, to look at molecules and predict how they might react based on first principles. Even complex stuff, maybe reactions you haven't explicitly been taught.
That sounds incredibly useful because organic chemistry isn't just an academic hurdle, is it?
Yep.
Well, it's everywhere.
It really is. It's the basis for drug discovery, material science, molecular machines, you name it. But if we're just testing recall, like a lot of current assessments seem to do, we're not building that deeper critical thinking needed for real innovation.
So instead of learning reaction recipes, mix A and B, get C, we need a more algorithmic way, a system for figuring out those curly arrows, the electron movements.
Yes. These priority rules offer that framework. They give you a structured way to find the reactive spots in molecules and predict where the electrons are likely to go. It gives you a starting point, a way into the problem.
What's the foundation for these rules? What do we need to know first?
Okay, so to really get these rules, we need basically 3 quick concepts under our belt. First up, inductive effects. We sometimes write that as plus or minus I.
Okay.
Think of this like a constant tug of war over electrons. It's based purely on electronegativity, how strongly an atom pulls electrons, and it works through the single bonds, the sigma framework. The more electronegative atom just continuously pulls electron density its way.
Got it. Like a constant background pull. What's next?
Next are mesomeric effects, or P in dollars, sometimes called resonance. Now, if inductive effects are that quiet tug of war, metameric effects are more like a big flowing river of electrons. Yeah, these involve moving electron pairs through multiple bonds, or systems with lone pairs, the pi system.
And these are generally more powerful.
Oh, much more significant usually. And they can operate over longer distances within the molecule compared to inductive effects. Very important.
Okay, inductive tug of war, mesomeric river. What's the third piece?
The third piece tackles a common conceptual hangup. It's about intermediates in a reaction. You often hear textbooks talk about stable intermediates.
Yeah, and that always felt weird to me. If it's stable, why does it keep reacting? Shouldn't the reaction just stop there?
Exactly. That's the confusion.
Yeah.
So we actually prefer the phrasing, energetically accessible intermediates. The point of a mechanism isn't to make something so stable it stops reacting. The point is to find the pathway that requires the least energy overall to get from start to finish. Accessibility, not rock-solid stability, is the key.
Energetically accessible. I like that. It makes more sense for something that's part of a process.
Precisely.
Okay, foundation laid. Let's get into the rules themselves. It's actually pretty simple when you boil it down.
Deceptively simple, really. At its heart, any organic reaction mechanism, no matter how complicated it looks, follows 3 basic conditions. You need electrons starting somewhere electron-rich.
Okay, like a source.
Moving to somewhere electron pool.
That destination.
And ending up somewhere, somewhere good or stable. We're going to formalize this with 5 specific priority rules that you apply in order.
All right, let's get into it. Level 1 priority rules. Rule 1, where did the electron start? Finding that electron-rich site.
This is the absolute highest priority starting point for drawing that first curly arrow. And there's a fixed hierarchy.
Okay, number 1.
Number 1 is a negative charge. Can't get much more electron-rich than having an extra electron pair sitting there. It's basically shouting, use me.
Makes sense. That's next.
Number 2 is an uncharged lone pair. Think of the electrons on a nitrogen in ammonia or an oxygen in water. Still very available, but maybe not quite as pushy as a full negative charge.
Okay, negative charge, then lone pair. What follows those? We get into bonds now, right?
Right. Number 3 is a multiple bond, which we call a pi system. Think double bonds, triple bonds. Those pi electrons are relatively high energy, more exposed, easier to get involved in reactions compared to single bonds.
And the last resort.
Number 4, the lowest priority starting point is a weak single bond, a sigma bond. Usually this involves bonds to large, easily polarized atoms like iodine or maybe strained ring systems. You typically only break these strong sigma bonds if there are no better options available.
So it's a strict order. If you have both a negative charge and a lone pair on the same molecule, the negative charge always dictates where the first arrow starts.
Always. Rule 1 is absolute in its sequence. Negative charge first, then lone pair, then pi bond, then sigma bond.
Got it. So rule 1 gives us the starting block. Now
Right.
rule 2, where do those electrons go? The electron pore site, the target.
Yep, where the arrow needs to point. And again, there's a priority order. Highest priority target.
I'm guessing a positive charge.
Exactly. Number 1 is a positively charged a carbenium ion, or just a proton, H+O. These species are seriously electron deficient. A carbenium ion only has 6 electrons around it, H+ has none. They desperately need electrons to get a full valence shell.
Okay, that seems straightforward. But the second priority target, this is where you mentioned it gets interesting and potentially confusing. It's an atom attached to a positively charged heteroatom.
Correct. Like a hydrogen attached to a positively charged oxygen or nitrogen.
Okay, hold on. Why not attack the positive heteroatom directly? Isn't positive the most attractive target according to priority 1 here? This feels like a contradiction.
That's a fantastic question because it hits on a fundamental principle.
Yeah.
The octet rule. Remember, atoms like oxygen or nitrogen want 8 valence electrons. Even when they have a positive formal charge, like an H3O plus add, that oxygen already has a full octet.
Oh, right. Okay.
So if your electron pair, your nucleophile, tried to attack that oxygen directly, you'd be trying to force 10 electrons onto it. That's a huge no-no in chemistry. Violates the octet rule big time.
So the attack has to happen nearby to sort of relieve the situation without breaking the octet rule.
Precisely. The arrow attacks an adjacent atom, usually a hydrogen or sometimes a carbon. This allows the electrons in the bond connecting that atom to the positive heteroatom to shift back onto the heteroatom.
Ah, so it neutralizes the positive charge by giving the heteroatom its lone pair back, satisfying the octet. Clever.
It's a crucial distinction for getting mechanisms right. So after positively charged C or H and atoms next to positive heteroatoms, what's the next level of electron pore site?
That would be number 3. A partially positive carbon or hydrogen, the delta plus ones.
Right. These occur when carbon or hydrogen is bonded to something much more electronegative, like oxygen, nitrogen, or a halogen like chlorine. That atom pulls electron density away, leaving the C or H slightly electron poor or delta positive.
Okay, so we have a start. Rule 1, a target. Rule 2. Now, rule 3, where does the electron density actually end up? The somewhere good rule, you called it. This stops us breaking that octet rule.
Exactly. When the new bond forms, something often has to give way. There are 3 main outcomes for where that electron density goes.
First one.
The simplest is if the target was a C+ or H+, Rule 2.1. The new bond just forms, quenching the charge. Mechanism might stop there. Stable bond formed. Done.
But if we attacked a delta plus atom, like in a carbonyl group.
Right. If you attack a delta plus carbon that's part of a double bond to a heteroatom, like CO, the electron density often shifts onto that heteroatom by breaking the pi bond. So the CO becomes CO-. That negative charge on oxygen is pretty stable. That's outcome number 2.
And a third way.
The third way is breaking a single bond, a sigma bond, usually to a heteroatom. This is what we call a leaving group. The incoming electrons force the electrons in that sigma bond to leave entirely with the departing atom or group. Think of Cl leaving.
Okay, so the electrons push out another group. Makes sense. That covers the main flow. What about the supporting rules? Rule 4 and 5.
Rule 4 is charge balance. It's basically just careful accounting. If a neutral thing, like an amine nitrogen using its lone pair, forms a bond, it must gain a positive charge.
And conversely, if a positive atom gets its lone pair back.
It loses the positive charge. Forgetting these charges is probably the single most common mistake students make when drawing mechanisms. Gotta balance the books.
And rule 5, iteration.
Yeah, this just acknowledges that reactions often happen in multiple steps. If your first mechanistic step, following rules 1 to 4, creates a new reactive site, maybe that O- we mentioned, or a new positive charge well, that new site might be the starting point for the next step.
So you just loop back, apply rule 1 again to the new situation.
Exactly. You keep applying the rules sequentially, find the best electron source, find the best target, see where the electrons end up, balance charge until you reach a stable product or run out of reactive species. The mechanism unfolds step by step following these priorities.
Okay, theory is great, but let's see it work. You mentioned an example, a key step in making salbutamol, the asthma drug.
Yes, a key step in its synthesis is perfect.
Yeah.
We start with a molecule that has a primary amine group, an NH2, and we react it with another piece that has a carbon attached to a chlorine atom, sort of like an alkyl chloride derivative.
Right, step 1, PR1.
The most electron-rich spot is the lone pair on the nitrogen of the amine. That's PR1, priority 2, uncharged lone pair.
Okay, where does it go? PR2.
It attacks the carbon attached to the chlorine. That carbon is electron core. It's delta plus because chlorine is electron negative. So that's PR2, priority 3, attacking a delta plus carbon.
Ah, and because we attacked a delta plus, we need PR3 immediately.
Exactly. To avoid breaking the octet on carbon, the CCl bond has to break, and those electrons move on to the chlorine atom,
Creating a chloride ion, Cl, and what's left with the main molecule?
well, the nitrogen formed a new bond using its lone pair, so PR4 tells us the nitrogen now has a positive formal charge, N+, and we also have the Cl floating around.
So we have a charged intermediate, N plus and Cl, that triggers.
PR5, iterate. Go back to rule 1. What's the most electron-rich thing now?
The chloride ion, Cl,
Yep.
it has a negative charge, so that's PR1, top priority.
Perfect. Now, PR2, where does it go? It's attracted to the positive nitrogen, but remember,
It can't attack the N plus directly. Octet rule violation. It has to attack an adjacent atom.
precisely. In this case, the easiest adjacent atom to attack is one of the hydrogens attached to the N+. The Cl acts as a base here.
So the Cl plucks off a proton.
Yep, it attacks the H. The electrons that were in the NH bond then move back onto the nitrogen atom.
Which neutralizes the positive charge on the nitrogen.
Right.
And we're left with the final stable organic product plus HCl, essentially.
Exactly. A clean two-step mechanism derived entirely by following the priority rules, including the iteration.
That example also neatly shows the choice that sometimes happens in PR2, right? The chloride acted as a base, attacking hydrogen, not as a nucleophile attacking carbon.
Correct. The electron-rich species often has that choice. Attack a carbon, be a nucleophile, or attack a proton, be a base. Now, for beginners, we often just tell them which role or regent plays to simplify things.
Reduces the cognitive load, as you said.
Right. But understanding why something chooses to be a base or a nucleophile, factors like sterics, electronics, that's where we need a bit more sophistication. That leads us towards level 2 rules.
Before we get to level 2, though, let's just connect this back. These rules feel intuitive, but what's the deeper chemical principle making them work? Is it related to those orbitals you mentioned earlier?
It absolutely is. Think of these priority rules as a very useful, practical shortcut. What they're really doing, in a rough way, is estimating the best possible overlap between the highest occupied molecular orbital, the HOMO,
Where the electron pair starts?
and the lowest unoccupied molecular orbital, the HOMO.
Where the electron pair is going.
Exactly. The reaction happens most easily when the highest energy electrons can flow into the lowest energy empty spot. So when we draw an arrow from, say, a lone pair on an oxygen, which is in a high-energy non-bonding orbital, the HOMO, to an empty porbital on a carbocation, the HOMO, that arrow represents the formation of a new, lower-energy sigma-bonding orbital.
So the rules are basically guiding us to the most energetically favorable HOMO-LUMO interaction without needing to calculate the orbitals themselves.
That's a great way to put it. You don't need quantum mechanics to follow the rules, but it's reassuring to know they're grounded in sound physical principles.
Okay, good. Now, complexity. What happens in bigger molecules where maybe you have, say, 2 different lone pairs or 2 different delta plus carbons? How do you choose?
Ah, yes. Now we enter the realm of selectivity. This is where you might have multiple sites that fall under the same priority level in PR1 or PR2. We need level 2 mechanistic selectivity rules to make the right choice.
Makes sense. Let's start with selectivity rule 1, where the electrons start. If you have 2 potential starting points, how do you pick?
Okay, here's a slightly counterintuitive one related to electronegativity. If you're comparing 2 different atoms as electron donors, say, comparing iodide, I, versus fluoride, F, acting as nucleophiles, which is better?
Fluorine is more electronegative, so maybe it holds electrons better. So iodide is better at giving them away.
Exactly. It seems backward at first, but the curly arrow means the electrons are leaving. The less electronegative atom holds its electrons less tightly, making it a better donor. So I is actually a much better nucleophile than F.
Interesting. What else affects the starting point choice?
Mesomeric effects again. If a lone pair is heavily involved in resonance or mesomeric stabilization, it's delocalized. It's spread out and more stable.
Making it less available to react.
Precisely. That's why an amide nitrogen is a much poorer nucleophile than an amide nitrogen. In the amide, that lone pair is busy being shared with the carbonyl oxygen through the +-M effect. It's less available to attack something else.
And sterics, bulkiness.
Huge factor, especially for the nucleophile versus base decision. Generally, less bulky reagents make better nucleophiles because they can physically reach the carbon atom they need to attack.
Whereas a big, bulky, electron-rich thing?
You might find it really hard to get close to an equally bulky carbon center. But a small proton, H+, on the periphery of a molecule, that's much easier to reach. So very bulky bases, like potassium terbutoxide, are great at removing protons, but terrible as nucleophiles. Sterics favor specificity.
Okay, so electronegativity, less a better donor, delocalization, reduces reactivity, and sterics, bulk favors specificity. Now for the destination. Selectivity rule 2, where the electrons move to. What if you have multiple electron pore sites?
Here it's mostly about figuring out which site is most electron poor, which has the largest delta plus charge.
And that depends on the surrounding atoms.
Entirely. Think about carbonyl groups again, CO. Is the carbon in a ketone more or less delta positive than the carbon in an aldehyde? It depends on what else is attached. Alkyl groups are slightly electron donating, +I effect, so they reduce the delta positive character. Aldehydes only have one alkyl group and one H, while ketones have two.
So the aldehyde carbon is slightly more delta positive, making it generally more reactive towards nucleophiles than a ketone carbon.
Correct. It's all about the subtle push and pull of electrons governed by those inductive and mesomeric effects.
And you mentioned a really cool connection here to biology.
Yes, it's fascinating. Why are proteins, the workhorses of life, built from amide linkages joining amino acids, not ester linkages?
Okay, why? Based on what we just said, the amide nitrogen has a +M effect.
Exactly. That nitrogen pushes electron density onto the amide carbonyl carbon, making it significantly less delta positive, less electron poor than the carbon in an ester group, which only has an oxygen's I effect and weaker +M effect pulling density away.
So the amide bond is just less reactive.
Much less reactive towards hydrolysis, breakdown by water, and that stability is essential for proteins to function and persist in the aqueous environment inside cells. Life literally relies on that subtle difference in reactivity dictated by these electronic effects.
That's incredible. So one more selectivity rule, rule 3, where the electrons end up. This seemed related to intermediate stability.
Yes. It's about ensuring the reaction proceeds through the most stable or energetically accessible intermediate. The source material prefers that term over the more technical Hammond postulate.
Why avoid Hammond?
It sometimes confuses students. They hear stable intermediate and think it means the intermediate is unreactive, which isn't the point. Energetically accessible focuses on the fact that the pathway to forming that intermediate is lower in energy, meaning the reaction is faster.
So the reaction takes the easiest route, the one with the most stable checkpoint along the way.
Pretty much. Think about adding something like HBr to an alkene. The first step is the alkene's pi bond attacking the H plus H. This forms a carbocation intermediate before the Br attacks.
And there are usually two possible carbocations you could form, right? Primary versus secondary, or secondary versus tertiary.
Exactly. And the rules predict you'll form the more stable carbocation intermediate. Tertiary is more stable than secondary, which is more stable than primary. Why? Because that intermediate is lower in energy, easier to form. That dictates which product you ultimately get.
So, putting it all together, these level 1 and level 2 rules give you a powerful toolkit. It's less about memorizing hundreds of reactions.
And much more about understanding the fundamental principles of electron movement, charge, stability, and shape. It lets you work out how molecules are likely to behave just by looking at them. You develop a chemical intuition, a feel for it.
That's like learning the grammar of chemistry, not just vocabulary lists.
That's a great analogy. If curly arrows are the language, these rules are like the phonics or the basic grammar. They give you the building blocks to become fluent, to read and write chemical reactions with confidence.
So the big takeaway for you listening is that you don't have to feel overwhelmed by organic chemistry. There's a logical system underneath it all.
Absolutely. These rules provide a step-by-step method to tackle mechanisms, even ones you've never encountered before.
Okay, final provocative thought time. We've built up this logical system. The level 1 rules, for instance, generally predict a mechanism called SN2 attack and leaving group departure happening at the same time.
Right, that's the standard outcome for many simple cases based on the priority rules.
But chemistry loves exceptions. There's another common mechanism, SN1, where the leaving group leaves first, forming a carbocation, and then the nucleophile attacks. The steps are in a different order.
Correct. And this is where the rules become even more powerful. By understanding the standard prediction from the rules, you can start to analyze why certain molecules or conditions lead to a different outcome, like SN1.
So the rules help you understand the exceptions, too.
Exactly. They give you the baseline. When reality deviates, you can ask, why did the leaving group leave first here? What made that carbocation intermediate so accessible, even though Rule 1 didn't immediately point that way? So here's something for you to ponder. Why might the order of steps change if your electron source, your nucleophile, isn't very strong and the carbylation that would form is particularly stable? Go look it up. It all loops back to those core principles of stability and reactivity.